So tonight we'll do some interesting questions dealing with compound interest, and then we'll look at being able to solve some equations, some exponential equations, without being able to get a common base. So last class we looked at rational exponents. We saw that the square root is the same as exponent of 1/2. Cube root is the same as exponent of 1/3. We talked about ripping apart rational exponents to evaluate them. And we saw that half-life and compound interest can be modeled with these types of functions. The compound interest equation is this. We saw this slide last time. Just like to take a quick peek at a credit card question here. A credit card charges 24.2% interest per year compounded monthly. That's actually not out of the realm of possibility. Let's say that there's $900 worth of purchases made on the card, and we're going to calculate the amount owing after 18 months. We're not paying anything on this. This is more or less one of those department store cards, or where you'll get no interest, no payments for 18 months. They will calculate the interest for you, but they won't charge you unless you're like a minute late. So in any case, if we see the word compounded, we're going to go right to the compound interest equation. And so what we'll look at here is having this equation. The 900 is what I started with. The 0.242 is the interest rate in decimal form. The 12 occurs in 2 spots because we're talking about a monthly occurrence for the interest. So we can simplify this. Take as many decimals as I can. You'll notice that we're looking for 18 months. But as we talked about last time, the t value is the time in years, so this needs to be 18.5. The way that I did that, by the way, is I took 18 months and multiplied it by a formula of 1. 1 year is 12 months. And so the months divide out, and I have 18 divided by 12, which is 1.5. So now I solve this, and the actual charges would be $1,289.21. So you can see that if you were 18 months and 1 day late, you would have been charged almost an extra $400 for that 1 day. And as somebody who's paid dearly for that, take my word, it can be just 1 day. But anyways, hence maybe why I'm teaching a night course. Okay, let's continue on. Here's a very similar type of question, but maybe it ends up being a little bit new. We're looking at an interest, a bank account earning interest 4.2% a year, but it's compounded monthly. Initially we have an investment of $400. When does it double in value? So as soon as I see the word compounded, I'm going to the compound interest equation like this. Oops. Now I'm looking for when it doubles. So my principal is 400. I'm going to double that to 800. I'm going to isolate the power. And now I'm solving an exponential equation. Again, I know it's an exponential equation because the unknown is in the exponent. And so I'm going to try and get common basis, but of course we can't here. So we're stuck, and this is going to take us pretty much all night to figure out how to do this. Isn't that great? So we can't get common basis, so what we look at here is mathematicians have invented logarithms. And so logarithms is a notation. It's not supposed to be something that makes sense to you, it's just the way we write it. And eventually these logarithms will prove fruitful in that we will be able to evaluate this expression. But it takes a while, so bear with me. So if we had 2 to the 3 equals 8, we know that the exponent is 3, the base is 2, and the argument is 8. So we're going to write this as, again, this is under notation, it doesn't make sense. We're just going to write it as log to base 2 of 8 equals 3. So you'll notice that we solve for the exponent. The 2 is the base, and the argument there is the 38. So we say this, log to base 2 of 8 equals 3. I'd like you to recognize that the 2 is a subscript. Please don't write this. That's something completely different. Okay, make sure that that 2 is a subscript. So we're just going to practice writing in log form. You'll see my little saying for this course is if you're stuck in one form, go to the other. And so here's a bunch of true statements that are in exponential form, and we'll look at writing those in log form. So again, what I would suggest here is that maybe you look at, allow me to do or show you the answers for a couple, and then you pause the video here and try some yourself. So the first one is 3 squared equals 9. So this is going to be log to base, well, the base is 3 of 9 equals 2. And then we have 36 to the 1/2 equals 6. We know that's true. That's going to be log to base 36 of 6 equals 1/2. Next one here we'll have log to base 16 of 8 equals 3/4. And this continues on. Now the last one, very similar to all the rest, except you may notice that I didn't put the base in. Now that's not a typo. What happens here is that when the base is 10, we don't have to write it. You can write it, but we don't have to. I won't write it. Now, of course, we'll need to practice going the other way. So log to base 81 of 9 equals 0.5. That's a logarithmic equation. That's the same thing as 81 to the 0.5 equals 9. And so you can see here, this is your base, log solve for your exponent, and there's your argument. So the next one here is 125 to the negative 1/3 equals 1/5, and etc., etc. And again, the last one here is the base is 10, the exponent is a negative 2, and so it's 10 to the negative 2 equals 0.01. So in general here, log to base b of a equals c, that can be rewritten in the exponential form as b to the c equals a. So let's take a look at evaluating some log expressions. Log to base 2 of 32. This asks 2 to the what gives you 32. Another way to say that is 2 to the x equals 32. We know this is 5. It's not 2 to the 5. Please don't tell me it's 2 to the 5. It's just 5. So log to base 2 of 32 equals 5. Log to base 2 of 32 is just another way of writing the number 5. Log to base 4 of 64, that asks 4 to the what gives me 64. So we know this is 3. So log to base 4 of 64 is 3. This one is not one we would know right away, perhaps. Log to base 1/4 of 32. So this asks 1/4 to the what gives you 32. So we don't know that. So what we would do here is we would get common bases. I know that 1/4 is 2 to the negative 2. And that's to the x. And 32 is 2 to the 5. And so now I have a power of power, so I'll keep the base and multiply those exponents. That's what I got here. And so I solve for x. X equals negative 2.5. But all of this was to solve for the exponent here, which is what that log equals. So you have log to base 1/4 of 32 equals negative 2.5. Question D is log 100. This asks 10 to the what gives me 100, and we know that answer is 2. So log 100 is 2. In fact, you can test that out. You can type that in your calculator, log 100, press equals, and it'll give you the answer 2. So let's take a look here at solving logarithmic equations. Log to base 2 of x equals negative 3. Well, what will happen here is if I'm stuck in log form, I'm going to go to exponential. So this is 2 to the negative 3 equals x. Well, we know that that's 1/8. Here we have log to base root 3 of 9 equals x. Again, stuck in one form, so we'll go to the other. This is root 3. This is root 3 to the x equals 9. And we found out last week that the radical of, or the square root is the same as the exponent of 1/2. Now I have a power of a power, so I keep those and multiply. My bases are the same, so my exponents are the same. Multiply both sides by 2. I get x equals 4. Let's just see there. So in the last examples, we had one question where we're solving for the argument, one question we're solving for the exponent. Now we'll look at solving for the base. So again here, solving for the base. So stuck in one form, let's go to the other. This is x to the 4/5 equals 16. And again, what happens here is that sometimes this looks a little intimidating. If this was x squared equals 16, as we talked about last week, you would raise both sides to the 1/2 to solve that. And if this was a x cubed, you'd raise both sides to the 1/3. Here, I'm going to do the same thing. I'm going to raise both sides to the reciprocal exponent. I'm going to raise both sides to the 5/4. And that way I have a power of a power here. So I keep the base and multiply those exponents. That's 20/20. So it's just x on this side. And now I can rip apart this exponent. Oops. And I see that 16 to the 1/4 is 2. 2 to the 5 is 32. So the x value here is 32. That means log to base 32 of 16 equals 4/5. Here's one log 1.3 equals x. Again, if I'm stuck in log form, I go to exponential. Wait a second though, the base is a 10 here. And my calculator can do that. Notice that if I had gone to exponential, I have this. The only way that I can do anything in exponential is by trying to get a common base. And I can't get a common base here. So exponential is no good. So the log form has to be good for us. And of course it is here because we have base 10. So we now know how to go from one form to the other. We know how to solve some log equations. Really, we solve the log equations by getting them out of log form. But we still don't know how to tackle this if we can't get a base of 10. But we'll deal with that. So here's a bunch of questions. Some of these are more difficult than others, and some of these you can look at and get these right away. But I'll go over each one, and I won't actually go over them with what's typed out on the PowerPoint. I'll kind of do these by hand, and that way you can kind of see what I'm thinking. I think that's the best way for me to do that. And I want you to recognize that each one of these is going to be a little bit different, and that means that there's no set kind of strategy for this. And one of the kind of overarching strategies is that if you get stuck and you can't figure out where to go, then quit. Isn't that great? Yeah, just give up. What I mean by that is give up, go try another question, go have a cup of coffee, go, do something else, and come back and you might see it right away. But sometimes in math you get an idea in your head and you keep trying to force it to work and it just doesn't. And so you need a fresh set of eyes to see it. So in any case, I'll do these. Here's question A. Log to base 2 of 32. Well, I know what that is. That says 2 to the something. Now I'll call it m here because x is already defined. 2 to the m equals 32. We know that this is 5. So this is 5. That is just 5. Then over here I have log to base 3 of root 27. So I'll say I'll say 3 to the something equals the root of 27. And the root is the same as an exponent as 1/2, as exponent of 1/2. And so I have 3 to the something equals 3 cubed to the 1/2. The power of a power, keep the base. Multiply those exponents, top by top, bottom by bottom. And so I see here that p equals 3 over 2. So I have 5 minus 1.5 equals x. So x equals 3.5. Question B, I have log to base 2 of x equals log 100. I recognize log 100. That says 10 to the what gives me 100. That's a 2. But now there's nothing else for me to do in log form. I'm stuck in log form. And when students ask me, Steve, I'm stuck here, I say, good, then you know what you're doing. So if I'm stuck in log form, I'm going to go to exponential. My base is 2, my exponent is 2, and my argument is x. So this gives me x equals 4. Done. Question C. Log to base 2 of 8 plus log to base 3 of 1 over 27. Now I'll just tackle that side for a moment. Log to base 2 of 8, I know what that is. That's a 3. That says 2 to the 3 gives me 8. This here, well, 3 to the what gives me 1 over 27. Again, if you need to write that out, 3 to the something equals 1 over 27. And 1 over 27 is 3 to the negative 3. So that's what my m value is. That's what this log is. And this equals, on the right-hand side, log to base 6 of x. So on the left-hand side, I have 0. Again, there's nothing else for me to do in log form, so I'm going to go to exponential. 6 to the 0 equals x. Anything to the 0 is a 1. X equals 1. Question D. I'm going to pick off each one of these logs. I know what each one of those is, or at least I have a way of figuring it out. The first one is a negative 1. That says 4 to the something gives me 1/4. That's a negative 1. This second one says 3 to the something gives me 81. That's a 4. This next one, log to base 1/5 of 25. I don't know what that is, so I'm going to do this over here. Log to base 1/5 of 25 equals some number. That means 1/5 to the m equals 25. This is 5 to the negative 1 to the m. This is 5 squared. So now I see that I have power of power, so I keep the base and multiply those exponents. Now my bases are the same, so my exponents are the same. So m equals negative 2. So this exponent, or this log right here, is negative 2. And now I have that, all of that equals, log to base 2 of x. So this, on the left-hand side, gives me just 1. So now I'm stuck in log form, so I go to the other form, exponential. 2 to the 1 equals x, therefore x equals 2. To the x equals 50. Well, I'm in exponential form here, and I can't get a common base, so I'm stuck in exponential. I'm going to go to log form. Log to base 10 of 50 equals x. Well, your calculator can do this. And I see, I just typed in log 50, and I get x equals 1.7. Question F. Log to base x of 4 over 9 equals negative 2 over 3. Well, there's not much I can do in log form, so let's get it out of there. X to the negative 2/3 equals 4 over 9. So again, I'm solving for the base here, so I'm going to raise both sides to the negative 3 over 2. Power of power on the left-hand side, so I keep the base and multiply those exponents. I'll have x to the negative 6 over 6 over 6. That's just x to the 1. This negative sign tells me to flip the base and keep the positive exponent. Now I'm going to rip this exponent apart. And the exponent of 1/2 is the same as the square root, so the square root of 9 is 3, the square root of 4 is 2. All of this is still cubed, so I have 27 over 8. Question G, 1/3 log to base 2 of 16 equals log to base 27 of x. Now, when I do this class face-to-face, a lot of students ask, well, what do I do with this 1/3? Well, how would you do it if it wasn't there? Well, I would recognize that this is 4, and then I would put it into exponential form. Well, let's do the same thing. This is just 1/3 times 4. So this is 4 over 3 equals log to base 27 of x. Now I'm stuck in log form, so I'm going to go to exponential. I'm going to rip this exponent apart. 27 to the 1 over 3 to the 4 equals x. This is 3 to the 4 equals x, so x equals 81. And lastly, question H. Log to base 2 of 5, which I don't know, equals log to base 2 of x minus 4, which I of course can't know because I don't know what x is. And you can stare at this one for a while. Or you can recognize that we have common bases. And if our bases are the same, then our arguments must be the same. And so we would say therefore 5 equals x minus 4. Add 4 to both sides, x equals 9. So now you've got some practice solving and working with these logs. Remember that when I say log to base 2 of 32 or something to that effect, that's just a number. So I always make the joke that you could give some of your phone number in log form. This happened to me once. I had only one time that a girl ever asked me for my number, and so I said, well, I got to be witty here, I got to be smart. So I wrote down my phone number in log forms. Instead of writing the number 5, I wrote log to base 2 of 32. And I'm sure the only reason why she didn't call was because she probably wasn't good at logs. So she probably got the number wrong or something. Has been always wondering what would have happened. Anyways, they're just numbers. So remember that you can, if you identify one as a number, if you know what that number is, write it as that number. So this whole conversation started with trying to solve an equation like this. And so now we can write this in log form. Log to base 1.0035 of 2 equals 12t. So that's as far as we can get. Whoa, that's weird. I don't know what's going on with that. So in any case, what we notice here is that 12t is the exponent. And so if this is equal to exponent, so must this be. So maybe there's laws of exponents that apply here to the logs. Now I'm going to do a derivation here. This derivation is not something you will be asked to do again, but the result of it is going to be true for all scenarios, and therefore we'll want to be able to use that. So let's consider the first law of exponents, which was multiplying powers. And when we do that with the same base, we keep the base and add the exponent. So if we had something like this, a to the b times a to the c, that equals a to the b plus c. So we know that's true. I don't know what's going on with my little pointer here. So now let's say that a to the b is x and a to the c is y. And this means that our original sentence is now x times y. And so if we put this in log form, we have log to base a of x times y equals b plus c. Well, what's b? B's right here. So if I take this and put that into log form, I get an equation for b. And the same goes for c. C's right here. So let's take this and put it into log form. So what we can now say is that this left-hand side, log to base a of xy, is equal to b plus c. Which means when I'm adding logs to the same base, I can keep the logs and the base and multiply the arguments. Or conversely, when I have a product as my argument, I can write that as the addition of those logs. So there's, one of the ways that I think about this is that logs make everything difficult and everything easy. Multiplication is difficult, addition is easy. Now it's not just the addition, you of course have to keep the log and the base. Otherwise we'd be saying something like this. 3 times 5, well that's 15, that doesn't equal 3 plus 5, that's ridiculous. But what we're saying here is log of 3 times 5 equals log 3 plus log 5. And you can test this out on your calculator. You can type in log 15 and see what that equals, and then go log 3 plus log 5, and you'll get the exact same answer. Now let's consider the second laws of exponents. When we are dividing powers of the same base, we keep the base and subtract the exponents. So if I have a to the b over a to the c, I keep the base and subtract those exponents. And again, let's let a to the b equal x and a to the c equal y. So our original statement now is x over y equals a to the b minus c. We're going to go to log form. Log to base a of x over y equals b plus c. We're going to do the exact same thing we did in the last derivation. We're going to take this and solve it for b, take this and solve it for c, because we have a b and a c right here. So what this means is log to base a of x over y equals log to base a of x minus log to base a of y. And so what I want you to think here is that when we're subtracting logs to the same base, we can keep the log in the base and divide those arguments. Or if you see the division, you see a log with the argument as a quotient, then you can break that up as the difference in those logs. So here's some examples. Log to base 3 of 189 minus log to base 3 of 7 equals log to base 2 of x. Well, I don't know what these numbers are. Like, this is a number, but I don't know what it is, and this is a number. I don't know what this is. 3 to the what equals 7? I have no idea. So I'm kind of stuck, except I see that there's common bases, and I'm subtracting the logs, so I can rewrite this as I can keep the log in the base and divide the arguments. And 189 divided by 7 is 27, and lo and behold, log to base 3 of 27 asks 3 to the what gives you 27. That's a 3. Stuck in log form, so we're going to go to exponential, and then we get x equals 8. In question 2, log to base x of 4 plus log to base x of 8 minus log to base x of 2 equals log to base 5 of 25. Well, first of all, I see that I have common bases. I also see that the right-hand side is a 2. So I'm going to write this as as log to base x of 32. And then I'm going to realize that I'm subtracting log to base x of 2, so I'll divide those arguments. This gives me log to base x of 16 equals 2. And I go to exponential form, and I see that x equals 4. So the third law, by this time, some of you are thinking, oh yeah, I don't believe him. He's talking hogwash here. This is all crazy stuff. But it's not really. We have a third law of logs. And so if we let n to the t equal a, and we raise both sides of the exponent b, we would get, what just happened here? Oh, sorry, I did that differently. If this is true, then what we have is this in log form. Now I'm going to raise both sides of the b, so I'll just put a b here, and I'll put a b here. Oh, shoot. I made a mistake. So the third law of logs is when we have a power of a power, we keep the base and multiply those exponents. So let's consider n to the t equals a. And so what we would have here is we could raise both sides of the exponent b. I know I have a power of power on the left-hand side, so I keep the base and multiply the exponents. If I go to log form here, I can write this as log to base n of a to the b equals b times t. Well, if I go back up to this expression, I can solve this for t, and I see that t equals log to base n of a. And so what happens here is that I can take this and plug it right back in there. And so what I get is log to base n of a to the b equals b times log to the n of a. Now, some of you are saying that this is hogwash, you don't believe me. Well, you can see right here that this is not baloney. That's a joke there, because that almost looks like baloney. Anyways, it's probably not one of my better ones. Or maybe it is, and that's a really sad state. But what I call this is the down and front rule. If I have a b here on the argument, or sorry, if I have an exponent on the argument, I can bring that down in front. And so what happens is, I call this the down and front rule, and we can do an example. We can have log to base 3 of root 27. Well, the square root is the same as the exponent of 1/2. So now I can bring this 1/2 down in front, and this simply becomes 1/2 times log to base 3 of 27, and log to base 3 of 27 is just 3, so this is 3 over 2. So this is a very powerful rule here, because we can take this now, our original equation, we can take the log of both sides, and that's a key thing to take the log of both sides, because now I no longer have 2, I have log 2. It changes everything. I no longer have 1.0035 to the 12t. I now have log of that. And so I can bring this 12t down in front. Remember, logs make everything difficult and everything easy. So this is an exponent. What's easier than an exponent? It's multiplication. And so now, because I've chosen the base of 10, and I chose that when I took the log of both sides, I can do this in my calculator. So what I can do here is I can divide. I did this all in one step. I divided by 12 log 1.0035, but you could have also divided, just by the log first. So I could add log to base 2 of log base 1.0035. That would have equaled 12t. And then I could divide both sides by 12, and that's what I get. You divide out. And so my calculator can do this. We can now solve this equation finally, an hour later. So in 16.53 years, this account will double in value. So what we can do now is we can take a little shortcut. We've seen that we had this, and we could write it like that. We also can take this and put it in log form, which means this and this are equivalent. So if I take and have a log form, I can evaluate that by changing the base. I can take log 2, there's my argument, divided by log of the base. So you have to remember that the base is on the bottom. And I usually make the joke that, you know, I don't know how you're going to remember that the base is on the bottom. I remember doing this years ago in high school, and I had this student who didn't get anything right all semester long. And I was making this joke, and the kids were, you know, they got it, the base and the bottom, it's all B's. But he raised his hand. I said, what's going to happen here? So I said, go ahead. Well, Mr. Shapiro, I figured out how I can get you to remember that the base goes on the bottom. I was like, oh, okay, yeah, tell me. Thinking, okay, it's just going to be alphabetical or just the same letter. He goes, well, the basement of your house is always on the bottom of your house. And I was like, yes, that is exactly right. So if that helps you, you finally got a question right. If that helps you remember that the basement of your house is on the bottom, please do so. But what's really important here is that by doing this, we can evaluate anything now. I can take log to base 3 of 28. We didn't know how to do that before. That's going to equal log to base 10 of 28 divided by log to base 10 of 3. And my calculator can do this. Which means we're unstoppable now. We can solve anything. For instance, we can solve 3 to the x plus 9 equals 100. Can't get common bases, so I'm going to go to log form. Log to base 3 of 100 equals x plus 2. I now know how to evaluate this. This is log 100 divided by log 3. My calculator does that. I solve for x. There we go. Again, I can check my answer here. I can plug this back in here, see if I get x, or see if I get 100. Here's the last one for tonight. 4 to the 7 minus x equals 80. Again, no surprise here, I can't get common bases. So I'm going to be able to go to log form. This is log 80 divided by log 4. The base is on the bottom. And then I solve for x. So we aren't quite done with the logs, but I think that's kind of enough. I don't want to overload you. I think it's really important that you go back and take a look at what these logs are, or maybe go through this again. This comes at you pretty quick, and then we're just going to use it. In the next session, it'll all be the old word problems and all that stuff, and the only difference is that by the end of it, we won't be able to get common bases, so we go to log form. But it's really important, I think, to go back and try some of these questions. Good luck.